Have you ever really thought about how we take the insane power of a lightning strike and somehow shrink it down to run your phone? It's kind of mind-blowing. Well, today, we are pulling back the curtain on electricity to show you the surprisingly simple rules that control this invisible force. You're going to see it's not magic, just some really clever physics.
Really think about that question. It sounds impossible, right? Taking this raw, chaotic, world-shaking power and controlling it with such insane precision that it can run the delicate little circuits inside your phone. Well, believe it or not, that's the exact puzzle we're going to solve together today.
Okay, so first things first. To really get a handle on this, we need to stop thinking about electricity as just something that comes out of a wall socket. Let's imagine it for what it truly is, a powerful, natural force. In fact, let's think of it like a huge, invisible river of pure energy.
So, at its very core, electrical energy is all about movement. But instead of water molecules flowing in a river, the things that are moving are these unbelievably tiny particles called electrons. And as they move, they carry energy with them. It's as simple as that.
This image here just lays it all out perfectly. You see that battery? Think of that as the pump, pushing those tiny electrons out and along the wire. They flow in this continuous loop, right through the light bulb, which makes it glow, of course, and then all the way back to the battery. That complete path, that's what we call a circuit.
Now, you can imagine that an untamed river of energy would be, well, pretty destructive and not very useful, right? So, the very first step in taming this force is figuring out how to control its flow. We basically need to learn how to build dams and gates for this river of electrons. Okay, so that leads to the big question. We've got this immense river of energy. How on earth do we actually control it? How do we build those dams? How do we make it do exactly what we want when we want it? Well, the answer lies in a property called resistance. And you know what? Electrical resistance is exactly what it sounds like. It's just a material's natural tendency to fight back, to resist the flow of electrons. Some materials are super easy for electrons to pass through, others make it really, really difficult. And we measure this opposition in a unit called ohms. And this visual, it just makes it all click. Look at the pipe on the left. The water's just flowing freely, no problem. That's like a good wire with low resistance. Now look at the right pipe, with all those obstacles slowing the water down to a trickle. That is high resistance. It is the exact same idea for our river of electrons.
And this whole relationship is wrapped up perfectly in a simple but incredibly powerful rule called Ohm's law. All it says is that voltage, and you can think of voltage as the push from the battery, is equal to the current, which is the flow of electrons, multiplied by the resistance. V equals I times R. This one little formula is the fundamental rulebook for pretty much all of electronics.
But here's the thing, just controlling the flow is only half the story. The real magic, the part that changes everything, happens when we figure out how to take that controlled river and put it to work.
And this is the part that is so cool. Resistance isn't just a brake pedal. It's not just about slowing things down. When those electrons have to really push and struggle to get through a resistant material, their energy has to go somewhere. It gets converted or transformed into other kinds of energy. This is where everything gets useful.
And here's where it all connects right back to your daily life. That electrical energy from the river is transformed by resistance into the heat that makes your toast, the light that fills your room, the sound coming from your speakers, or the motion that spins a fan. It is all resistance, hard at work. Just think about a toaster for a second. Those wires inside that glow red hot? They're made of a material with super high resistance. The electricity has to fight like crazy to get through, and that big struggle converts the electrical energy into intense heat. It's the very same idea in an old light bulb filament. Resistance is what creates the function. Okay, so we can start the river of energy, we can control its flow, and we can make it do work. But what if we want to save some of that energy for later? For that, we need another tool in our kit. We need a way to build a reservoir. Because let's face it, a steady, calm river isn't always what you need. Think about a camera flash. For that, you need a massive, instantaneous burst of light, like a controlled flash flood on demand. So how in the world do you store up energy for one giant sudden release?
The answer is this little guy, a capacitor, and its design is just brilliantly simple. It's basically two metal plates separated by something that doesn't conduct electricity. That's it. This super simple structure allows it to build up and store an electric charge, kind of like a tiny battery that can charge and discharge incredibly fast. And we measure a capacitor's ability to store that charge in a unit called the farad. So the higher the capacitance, the more charge it can hold, and the bigger the energy reservoir it can provide for a circuit.
And their uses are, well, everywhere. They help tune your car radio to the right station, they smooth out the power going into your sensitive electronics, they even prevent sparks in your car's engine, and yep, they provide that massive burst of power for a camera flash. Just look at all these different shapes and sizes. Every single one of them is a capacitor. You've got the big, can-shaped ones you might find in a power supply, all the way down to the tiny little ceramic ones you'd see on a computer motherboard. These little energy reservoirs are absolutely everywhere.
So let's bring this all home. We've got a flow of energy, we have a way to control it, a way to transform it into work, and a way to store it. These simple concepts, these are the fundamental building blocks of pretty much all modern technology.
This slide really recaps our whole journey, doesn't it? Step 1, you start with a flow of energy. Step 2, you use resistance to control that flow. Step 3, that resistance transforms the energy into useful work. And step 4, you use capacitors to store it up for when you need it. That's the whole story, right there. And here is the most incredible part. You take something simple, like a flashlight, and something wildly complex, like a supercomputer. They seem like they're from different planets, but they are built from the exact same handful of principles we just talked about, just combined in more and more clever ways. You see, these aren't just abstract ideas in a textbook. They are the rules to a toolkit that has literally built our entire world. So the final question isn't really about what other people have built. It's about you. Now that you know the rules, what would you build?